Hello everyone, can you hear me okay? Because I have the lavalier mic on and there will be a dancing show here, so I move around a lot. Well, I want to thank John and Harvey and the rest of the iMAPS Symposium leadership for inviting me here today. I've worked at Analog Devices a long time. I've worked in a bunch of different fields, and most recently I'm in autonomous driving now. And I could tell you that that's a very interesting field, and it's ripe for innovation, especially in the advanced packaging realm. So I hope to give you a little bit of a flavor about what the challenges are in this space. We'll talk a little bit about what Analog Devices is doing as well, because I think it's some pretty cool stuff that you would like to hear about. Also, as an interesting note, in this particular facility, Analog Devices actually had their general technical conference about 20 years ago. And today, the conference rivals the size of ISSCC, which is the International Solid State Circuits Conference out in San Francisco. So, we started here with, much in the same way that, that you guys are, but obviously, through a lot of the innovation that we've been able to bring to market, we've been very fortunate to, now have these big conference centers down in downtown Boston, where we're holding this conference. But it's great to be back at this location. All right, so still, everybody okay? You can hear me for the most part? Okay, so let's get going. So a little bit about Analog Devices. So, ADI has been around for over 50 years. It's one of the very few companies in the semiconductor industry that have been around that long. We all know that our industries and industries associated with semiconductors just require a constant reinvention of themselves in order to stay relevant. If you look at Analog Devices history, we were selling, modules largely, with discrete transistors to realize op amps and different kinds of linear functions. We then, in the 60s and the 70s, we went into traditional monolithic semiconductor engineering, and we started to do a lot of products based on the advanced deep submicron nodes. Most recently, we're getting down into 16 nanometer and 7 nanometer technologies. And now, as we move forward in this next realm, we're bringing a lot more system solutions to bear. One, the semiconductor technology itself can embody a lot more functionality than ever before, given a lot of these deep submicron capabilities. But also the advanced packaging technologies and system in a package capabilities that are now realizable today in large-scale operations that really is allowing ADI to bring a lot more technology to market. So when we look at overall in terms of what we are doing as a company, we involve ourselves in problems that are difficult to solve, and we like to work with customers that disrupt the market. So as we go through this, these are tough problems, that I'm hopeful that we all can work together to solve. So what are we doing these days in this space? And if you look at ADI's history, we've been involved in these automotive safety applications for over 20 years. We were actually the innovator of the first monolithic airbag sensor. Before that, and before in the early 90s, it was a purely mechanical system. And so going to a monolithic sensor, the ADXL50, which was a MEMS sensor, that revolutionized the industry. 2 years later, Congress made it mandatory that all new automobiles have airbags on them, largely because ADI was able to bring down the cost point and keep the functionality and the performance where they needed to be for these safety critical applications. And so again, it's a real great opportunity here to, in the future, as we drive into newer applications outside of what we call protective safety, like what we did with the ADXL50, into predictive safety, things like radar and LiDAR technology. So ADI is a technology company. We have, basically the way that I like to think of ADI, it's a tree where the core of that tree, or the trunk of the tree, is core technology like RF, photonics, advanced packaging, things of that nature, and the branches are the applications that we can apply that technology to. And so we've been involved in RF applications for over 2 decades. Looking at different base station, military, aerospace applications, and now we're bringing that technology down into automotive. And then also in photonics, laser LiDAR systems are becoming, much more needed in these autonomous systems. And so ADI is bringing a lot of technology to bear. And we recently had an acquisition in this space, Vescent Photonics, which I'll tell you about a little bit later, bringing solid-state laser beam steering technology, which is a very important technical problem that we have to solve in these applications. Okay. So a little bit about the mega trends associated with autonomous driving. This is, when I have to go in front of my CEO and I have to tell him, why is this stuff happening? What's going to happen? What are the precursors to, to fully autonomous driving, which is still, frankly, several years away on this. But if we look at this, it's clear that alliances and partnerships are driving a lot of the innovation. There's not one single company that has all of the technology to be able to bring an autonomous vehicle to market, right? And there's a lot of, some vertical integration going on, but there's a lot of bets being made in terms of the component pieces of technology. And so you see all of these partnerships springing up. A lot of money coming around on this. GM buys this cruise automation for $1 billion. Aptiv, who was Delphi, buys Nutonomy for $500 million. Zero revenue for Nutonomy, just maybe 20 guys. I would have loved to be part of that startup. So now we're seeing robo-taxis pop up all over the place. That's going to be the first embodiment of these highly autonomous systems. You see Phoenix, that is a proving ground for a lot of these different modalities of what we call level 4 and level 5 driving, where basically the driver is removed out of the equation here on this. Why did they choose Phoenix? Well, it's sunny, it's flat. And it's a pretty easy problem to solve from an autonomous driving standpoint. Having said that, I think we've all heard of the recent Uber accident down there. That was a catastrophic failure of the autonomous driving system here. And so there's still a lot of work that needs to be done in order to mature this technology. It's a very unfortunate accident, but frankly, as an engineer, I want to work on that problem, because this is all about saving lives. And if we can make that a more robust solution, I think we're all going to benefit from it. What we're seeing is an increased utilization of autonomous machines. So we just spoke about Uber, and those are safety critical applications that human life is involved. When you look at drones and different types of autonomous machines in agricultural, industrial settings, those are more benign settings. Still very complicated in order to develop technology, when it comes to hardware, sensors, and software to navigate those particular applications, but they're not safety critical. All right, so that has the benefit of maturing the technology. It also allows the regular people in this world to gain an appreciation and a comfort with the technology, right? Because the autonomous driving is a huge change in modality and how we actually move about. And it takes a lot of trust in the actual machine that's doing the driving. If we could do more in this space here, I think it's going to aid the adoption of the technology overall, and I'll tell you a little bit more about that. And what I'm going to talk to you more about today is this concept known as sensor fusion. Sensor fusion is the concept that not one single sensing modality is going to be sufficient in order to operate an autonomous vehicle. Cameras can't see at night. Think of it like that, all right? But radars can. All right, cameras can read street signs and see colors, right? LiDAR systems cannot. So there's a lot of benefits to each of the sensing modalities, and I'll go into that a little bit more here today. But the upshot is that not one will work, and you need to fuse these technologies together in order to develop a 360-degree view around the car and give you a trusted position in three-dimensional space. So, if we look at the primary sensors that are used in these automobiles today, you can see vision. Vision is plentiful in many of the automobiles today. In fact, backup cameras are now standard fitment on automobiles. All right, so cameras are definitely part and parcel to autonomous systems, but they have strengths and weaknesses. They're very good for object detection and classification. They can see with a very fine resolution. But obviously, inclement weather, low light, they fall down to some extent here. So we have to complement that weakness with a strength. If we look at radar, It's much more robust when it comes to seeing through bad weather. And so you can use it very much for object detection. There is something here. Now, going to object classification, there's something here. It's a bike, it's a person, it's a car. You know, radar is going to run out of steam to some extent because the resolution of the radar systems are not sufficient in order to discern these types of objects far out in front of the automobile. Still, I'll tell you a little bit more about what we're doing in this space in order to drive to that superior resolution. LiDAR systems are, you see these in many different applications today, like precision mapping and different types of mapping of geography. It is one of the highest resolution technologies available there for those types of applications. But they are plagued by significant issues. LiDAR does not like rain or any kind of reflective particulate in the air, and so we need to somehow get around that. Also, many of the LiDAR systems are based on what's known as the 900 nanometer wavelength, because that's where the lasers and photodetectors are today. There's output power problems with that because you can actually see the laser beam. And so there's only so much output power that can be put onto these lasers, and so it leads to eye safety problems, which limits the overall performance of the system. And so we'll talk a little bit about how we're getting around that. One of the unsung heroes of these types of autonomous systems is what's known as an IMU, or an inertial measurement unit. So this is a MEMS device which measures inertial motion, and it can also be fused with the GPS signal in order to give you a trusted position in three-dimensional space. This is a very interesting technology because it's impervious to all of the other environmental conditions that I was talking about here: light, dark, rain, bad weather, whatever it might be. Gravity is constant. That is one thing on this planet that I think that we can all count on, and the IMU takes advantage of that to ensure that when you're driving your car inertially with a GPS signal and a precision map, it will keep you in the lane if all of your other sensors fail. So again, this is all about redundancy and sensor fusion in the system. And so when you look at this, there's this kind of potpourri of technology here that we have to bring to bear to solve this problem. Let's look at the car today. So today, you know, in the automobile, you have, you know, several ultrasonic sensors. So these are the little bullet holes in your bumper that you have in order to aid in your parking. I can tell you that car companies absolutely hate those types of things because they may be cheap, but you have to keep inventory for every single color of an automobile. And so maybe the technology is cheap, but the inventory holding costs are huge on that. So they're trying to get those out of the automobile. You have several airbag sensors, you know, whether it's on the B pillar of the automobile or on the front of the automobile, in order to you know, detect a crash in certain instances. And then maybe you have a front range radar or a front facing radar here for in some of your more premium automobiles on this, and a backup camera here. And then there's some central ESC, or electronic stability control gyro, in the center of your car that manages, when you go around turns, to make sure that the stability of the automobile is kept in check. But going forward, you know, as we work with these car OEMs and we look at the you know, the technology of the future, the car looks more like this. So anywhere, you know, in your car, you're going to have anywhere from 6 to 10 radar sensors with different types of frequency modalities that would be able to take advantage of both short range and long range needs here. You're going to have several LiDAR systems, whether it be a time of flight system for short range or a long range scanning system here in order to develop a more comprehensive view around the car. You're also going to continue to have cameras, but perhaps not as prevalent as you would think. Right, so cameras are very good visually, so you can see them here. Perhaps there'll be an e-mirror technology that cameras will actually replace your rear view mirrors. You'll have a front-facing camera here and a rear-facing camera, but radar and LiDAR is a very, very important technology to fuse with that existing camera data here. One thing that's interesting is that this big processor is starting to appear in the center of the car. So NVIDIA, who used to develop graphic processors for high-performance video game applications, well, they are now getting into the gig of developing GPU processors for artificial intelligence systems for automobile. It just so happens that the technology and the fabrics used in GPUs, or general processing units, are very appropriate for both of these types of applications. And so they've done a huge pivot to this. So this is very interesting because this GPU processor is the artificial intelligence engine behind the autonomous car. And so the algorithms sit here, but the high fidelity sensor data is all moved here, and this is where the sensor fusion happens in the center of the car. So you see, we are at this inflection point of where this technology is going here, and how the automobile itself is going to fundamentally be reshaped in order to accommodate these types of high-performance sensing systems. So what are we doing in this space? If you look at ADI, as I mentioned, we work on the hard problems. And so if you look here, we don't do cameras. That is not something that ADI does. Camera technology has been around for over 20 years. We have a lot of very strong partners in this area, Intel being one of them. They spent $15 billion to acquire this company known as Mobileye. So there's a lot of investment already in this space, and in my view, very little areas for differentiation. And also the technology is mature and appropriate, I think, for automobiles today. But if you look at radar or LiDAR or even high-performance inertial MEMS, there are huge performance gaps from where we are today to where we need to be. And I'll tell you a little bit more about that on it. But ADI's goal here is to solve these difficult technical challenges. And as I mentioned in the previous diagram, when you look at artificial intelligence systems, it's garbage in, garbage out. If you bring in inferior sensor data, your artificial intelligence algorithms will not be trained properly. They will not understand the environment around them very clearly because they would pick up different kinds of noise artifacts that should not be there. And so you need to have the highest fidelity sensor data in order to properly train these artificial intelligence algorithms of tomorrow. And that's a big piece of where ADI plays. We are hoping to be the foundation upon which these types of autonomous systems are based. Okay, so we're going to get into a little bit more technology now. So I wanted to give you a little bit of a primer on Automotive Radar. Again, many of you guys have these in your cars today, blind spot detection or lane change assist. These are based on the 24 gigahertz frequency modality. Basically, what that does, if you do the math, based on the 200 kilohertz bandwidth that's available, that has been allocated to that particular frequency band, you can see down to about 75 centimeters, right? Again, when you drive your automobile today and you have your blind spot camera on, you basically see car. That's it. And sometimes you don't even pay attention to it because the system is faulty to some extent. So there's a lot of improvements that we're making in this space, and so we see the whole industry moving to 77 and 79 gigahertz, and that poses some very interesting challenges and opportunities for all of us in order to do this. So firstly, when you go down to 77 or 79 gigahertz, you are able to discern a much finer range resolution than what you would be able to in today's system, down to upwards of 3 to 3.5 centimeters. Why is that important? If you're looking 200 meters out in front of the car and you see a truck, and next to that large truck there is a small child, how are you going to be able to discern those two things? In radar systems today, it just looks like a big blob. But if you can have the range and angular resolution here that affords it, in terms of the way that we're doing the architecture and the frequency band, you will be able to discern those small objects that are in the presence of large objects. Again, a very important piece of how we need to improve these systems of tomorrow here. So if we look at what ADI is doing in this space, and as I mentioned, going down to 77 and 79 gigahertz is a unique opportunity. So one, you've seen the number of radar sensors in the car going to explode, anywhere from 1 to 0 today to 6 to 10 tomorrow. So I'm going to tell you that we're going to have to put more things on that chip in order to proliferate these radar sensors. So ADI's strategy is to go to a deep submicron technology platform. This is really hard. RF millimeter technology on a standard bulk CMOS process is a very, very difficult technical proposition. But we have been able to achieve this and are sampling today. We are calling this technology more of an imaging radar, because the idea is that, versus just an object detection, you will be able to actually start to classify these objects given the superior performance. And even classify intent. It's not only a bike, but it's a bike that is going in a certain direction. So from that standpoint, it makes the reaction time associated with these algorithms much better, because we're able to do a lot of the pre-processing given the high fidelity data stream that we're getting off of these transceivers here. One of the other things that's very interesting is going from 24 gigahertz to 77 and 79 gigahertz, the whole wavelength shrinks. So there's a lot of very interesting things that we can do with that. If you look at a 24 gigahertz module today, it's roughly the size of a small book, just because the antenna has to be spaced as a certain multiple of the wavelength that it's trying to capture. All right, 77, much smaller. And so here we have a low temperature coefficient ceramic solution here with a 3 transmit, 4 receive solution with a surface mounted RF transceiver on. That's a dime that's next to it. And so the idea behind that, one, I can mount this thing and all of the RF connections are just taken care of. I don't have to use any kind of Rogers material or really challenge my customers on that. Basically, I can overmold this whole thing with plastic and its power and digital data that comes out of it, which allows my customer to pepper these things around the automobile. All right, so again, this is a lot of advanced development that we have in this place, but the idea behind this is moving from more these discrete solutions, they're clunky, they're large, they're not reliable, to much more sleek solutions that bring a lot of high performance, because we can integrate all of this technology in a very small form factor overall. And so these are a lot of the things that we're working on today. This is a wide bandwidth antenna over the full 5 gigahertz spectrum. Again, that's a very difficult thing to develop here. LTCC offers very fine, offers a lot of capability for fine lithography. So again, moving more into this space here with the advanced packaging capability. I also wanted to share with you another acquisition that we've been doing in this space recently, and you could tell ADI is really moving, in order to provide these larger types of system solutions to customers. So there's this company known as Simio in Germany, and they actually had radar systems today that are driving autonomous machines. So things like autonomous tractors or autonomous port cranes. So remember what I was saying in the beginning, these types of applications are really going to serve to de-risk these algorithms, de-risk the technology overall. And they're very visible in certain areas where people will gain more comfort with the technology. So these systems exist today, globally deployed worldwide, and managing a lot of these industrial applications here. So this is a little bit more, about what we're doing in this space. So this is, based on the industrial frequency band, because again, when we look at 77, 79, that's unique to automotive and automotive infrastructure. But still, this offers anywhere from 1 to 7 gigahertz of spectrum that really gives us a lot of room to play with in order to hit the performance that's needed. These are full solutions. And that's important because, we might talk about automotive, and when I go see my automotive guys, they have a team of 50, 60 guys that are doing RF millimeter wave engineering. They're also doing a lot of algorithm stuff. If I go see a guy that's developing systems for trains or precision agriculture or things of that nature, they don't have those guys. They need to have something right away that they can just mount, and get going on. And that's what this technology affords here. In fact, these things are so ruggedized, they are hermetically sealed, they are large, so you can actually use them as ladders, because that was actually a requirement for this particular product here, so people could walk up these scaffoldings, and they're out-of-the-box operations. You put it on, you mount it, and automatically you can communicate it with it over Ethernet, and you can get a lot of the visualization software. So again, this is a full package solution that we can use in steel mills, precision agriculture, and it works under the harshest conditions. And so we bought these guys because, one, they have really great technology, not only from a hardware design perspective, but all of that complicated software that's behind there that's doing all that object classification and detection, that's already done here. and it's being deployed in these harsh environments. And so when I look at my technology and what we were able to acquire here, this is going to accelerate the innovation, and we're really going to be able to bring something to bear to market that I think is going to be very interesting. So that's the radar story here. Now, I'd like to talk to you a little bit about LiDAR. You may have heard that, LiDAR has a mixed bag. If you listen to Elon Musk at Tesla, no LiDAR. We don't need LiDAR. That technology is not relevant to these Tesla systems. I could tell you that Elon Musk said the same thing about radar before that unfortunate accident in Florida where a Tesla actually hit the side of a semi. Why did that happen? Because the side of the semi was white. It was traveling orthogonal to the direction of travel of the person that was killed, and the white side of the semi looked like the horizon. And so that's why the camera failed, because it just assumed that that was the horizon. I could tell you if it had a radar, it wouldn't have happened. Strangely enough, we're now working with these guys on radar technology, but that's good for everybody, right? So, but LiDAR is a very important piece of technology because, as I mentioned, it affords a capability that radar can't. If we look at angular resolution, for example, radar is anywhere from 1 to 3, and you could, with some techniques around MIMO or multi-in, multi-out, which is a communications technique, you could probably get to sub 1 degree angular resolution. But LiDAR systems can provide sub 0.1 degree angular resolution, which again allows you to be able to properly detect and classify these types of objects around the automobile. But you don't see these in cars today. Okay, these things are very expensive. Today, for example, these spinners, which you may have seen on a Google car or something like that running around the street here, those are between $8,000 and $10,000. All right, so there's clearly that's not going to be something that is going to find its way into these automobiles of the future. So there's a lot of innovation that needs to be brought forth here. And so you'll hear, we talk about LiDAR, we talk about solid state and being able to miniaturize these solutions, into a much smaller form factor in order to support the mounting on the automobile. And there's been some attempts, in this system. So MEMS mirrors, the TI DLP technology, which was in the consumer space, where you can use a MEMS mirror in order to steer the direction of the laser beam. Very interesting technology. Not really good when you have it on a road and you have vibration, to some extent. How are you going to be able to compensate for that? Because it's still a mechanical system. Optical phased array, one of the unicorns in Silicon Valley, named as Quanergy, has brought this technology forward. Very interesting technology. Fully solid state, a lot of power consumption in order to calibrate the array. And so again, a lot of innovation that needs to be brought to bear here in order to address these challenges. But again, a lot of money being poured into this. So what are we doing here? Well, we have decided to take a different approach to the beam steering. And so our technology is based on what's known as a liquid crystal waveguide. And I'll explain what that is in a moment. But it is a fully non-mechanical beam steering. There is absolutely no moving parts in this, which is very important for automotive robustness overall. Nothing should be moving other than the drivetrain and the tires on the car, frankly. But it also offers what's known as intelligent adaptive scanning, and I'll explain that, how we do that next. But it operates like the human eye. And so your human eye is able to focus in on a particular object and provide a high resolution view, but it kind of throws out a lot of the information on the periphery, which is very important in order to manage the overall data system of the car. And so this affords that to some extent versus having to capture everything and then filtering things out later. Again, improving reaction time and the quality of the results. So we have a long-range system here, which I'll explain, but we also have to complement with a short-range system. And so this is a time-of-flight solution, which is based on a charge-coupled device. But, that's less interesting technology in my view. I'd like to talk a little bit more about the solid-state scanning problems. So if you look at this, when we say, okay, what are the packaging challenge? What are these integration challenges? This is a LiDAR signal chain today, right? I'm not going to bore you with the details, but there's a lot of chips in here. All right, so unlike when we looked at radar, right, where, okay, we're getting down to 77 gigahertz, we have to start putting more and more things in these modules, we have to make them much more capable, and, this is where 28 nanometer and different types of technologies come in. LiDAR is in just its infancy, so we're building it out with Lego blocks today. All right, and that's how the industry is actually looking at it. I was told by one of the professors down at MIT that the 3 phases of innovation is to make it work well, and then make it work cheap. Those are the 3 phases. We're kind of in the make it work stage at this point, right? So again, we have a lot of existing technology here, and we've addressed some of the fundamental pain points associated with steering the laser beam that I think is going to be very important. One of the other things that it's interesting to note here is that we're focusing our work on the 1500 nanometer wavelength of light. Remember I told you about 900 nanometer being in the visible light spectrum, and it limits the output power, therefore the range of the LiDAR system. Going to 1500 nanometer, you're out of that visible spectrum, and that affords you to basically put out 4 times the amount of output power. What does that mean? I can see out in front of the car more clearly and much more far. And so that's an important piece here, but that brings a lot of challenges, into the system. Not only on the beam steering side and the laser side, but also on the photodetector side, because photodetectors at 1500 nanometer are not readily available today, in an automotive qualified version. So we're working on a lot of that here. But you can see here, bringing this all together, this is going to be tough. All right, a little bit more on the manufacturing challenges and what exactly is a liquid crystal waveguide. A liquid crystal waveguide is not unlike the liquid crystal matrix that you see on your PCs today. And we like that because that means that it can be built pretty cheap, right? Because PC displays and different LCD displays are, pretty robust from a manufacturing standpoint. But if you shine the laser beam through the plane of the display and put a high voltage potential across it, you change the index of refraction of that matrix and you can steer the laser beam. So it's very elegant in its operation. It's pretty damn complicated in how to build it. But again, we like that to some extent. So, it's very interesting because it's truly solid state, no moving parts. Robust to shock and vibration. The MEMS mirrors have a lot of those issues, and I mentioned the adaptive scanning and the blind spots that come with other systems are not plagued here. But if we look at how we're going to build this thing, you can see here that there's an angle of this facet of this liquid crystal waveguide that has to be precision manufactured. All right, and there's a lot of challenges associated with that overall in order to maintain this type of tolerance. And the roughness is obviously very important because the laser beam is going through it, right? So you can't make this too rough, otherwise it will disperse the actual beam of light. So there's a lot of challenges associated with just manufacturing this. And this is probably, I would say, a 1/2 inch by 1 inch. These things are very, very small, completely unlike that big spinner that's sitting on top of the car today. So if you look at some of the other things, that we're putting together and how we're going to construct this. So, up here you can see, okay, we have a laser, coupled with the actual waveguide. There's a huge challenge associated with the alignment of these types of optical components. You're pumping a lot of current through this laser here, and so you have to really minimize the inductance of the entire system. We have a thermoelectric cooler here because, again, we have a laser here that's pumping out a lot of current. We have to basically get the heat out of the system here. Fortunately, one of the issues with liquid crystal waveguides is that they don't work too well in low temperatures. Right? You've seen this in your display in your car before, that the response time is directly proportional or inversely proportional to the temperature. And so having an active thermal management system in order to minimize the operation temperature is a very important piece of the innovation here that we're bringing to bear. On the bottom here, we have a couple receive concepts here. So an arrayed photodetector array with a transimpedance amplifier behind it. These things also need to have minimal inductance associated with them. And so we can build these things in a stack configuration like you see here. And there is a micro lens putting on top because we have to focus the light. Right, that's another piece of what we need to do here. We need to focus the light on that very small photodetector here. So there's a lot of challenges here, when we look at the LiDAR system overall. All right, that's the LiDAR story. How am I doing on time? 44 minutes, okay. So just a couple more slides here. So I wanted to kind of give a plug also to these Inertial MEMS products. So again, as I mentioned, they're the unsung hero of a lot of these systems today, but they are also absolutely fundamental to these cars. They are the cornerstone of the crash system that are on every car that is built in the world today. Airbag sensors and most recently stability control, which is very prevalent here in North America and the EU, just starting to take off in China. But we have been in this space for over 20 years. And so we actually do the inertial measurement units that go on aerospace and defense drones and different types of high-end applications. And now we're bringing that technology into the automotive space. All right, because if we can fly a drone, that technology or that performance is actually appropriate for these types of applications. And as I mentioned, this is very important for what's known as dead reckoning. If everything else in your system fails, are you going to continue to go in the direction that you're going in? And again, you can fuse it with a GPS signal and a precision map. Again, you're not going to operate without the eyes of the car, your radar, your LiDAR, and your camera, but it provides the backup in case it's caked with snow or you have some kind of catastrophic failure. It will be able to pull you over to the side of the road safely. And so these systems are going to be much more prevalent in the automobile of the future. One thing that's also interesting about this MEMS technology is what's known as condition-based monitoring. These cars in many different modalities are going to be driving 24 hours a day. It's a much different use model than what's being used today, where most of the time the cars are parked out in the parking lot. And so now you need to monitor the health of the car. So ADI has done a lot of work in condition-based monitoring, where basically it's a vibration sensor that you could put on your car, and if you start, if things start not necessarily feeling right in the automobile, it's basically a system health check. So again, we can do preventative maintenance, right? And so when things start to get unhealthy, we can address them before they fail. So again, that's a very important piece. You have to fail operational in these systems. So, why is an IMU important? And so this is a little bit of a simulation that we did here, and we compared what was an ESC grade gyro, or an electronic stability controlled gyro, which you have in your automobile today, and IMU that is not calibrated at all. And so you can see here, this is a route in Wilmington, Massachusetts. We ran it around the ADI campus here. The blue line is basically if you... And then we basically took the IMU and we did the same thing, uncalibrated, just out of the box. And you can see here that it's a much better solution overall. Now again, uncalibrated, so there's a lot of work that we can do in the software and algorithm space here in order to bring that into line, and also with sensor fusion bring this into bear. But again, when you look at this, this type of performance is very difficult to achieve. What the gyro actually looks like. Why do we do that? We need the highest performance gyro, so we have to mount one of them. Actually does all of the cross-action. Rigidity in the system, and also to make it very mechanically in order to stiffen the entire system. And the idea is that we put it together in a very to allow our customers to mount it to the board in a very robust way, and then we put this liquid crystal polymer cap, put some stabilizing bars in. What we see in some of these advanced drone applications. Again, that microprocessor there's a lot of things that we could do with that to fuse the data together to keep that high performance going. The simulation I showed you last time, all that was one of the high performance gyros. But again, if you put this all together and you put an algorithm around it, all of a sudden you're cooking with gas. All right, so I kind of want to leave you. This is my last slide here, and you know, this is a call to action to all of us here. You know, this is a changing landscape in what we're dealing with here. The amount of, you know, investment that is going on in this space, the amount of innovation that is being brought to bear in these applications, the gaps that we see today, you know, this is really you know, an opportunity for all of us. So one thing, performance is valued. All right, and that's a very important, you know, thing, right? That means that we're going to get paid for the innovation that we provide, you know, in these systems. These are not commoditized systems. They are not perfect today. They are not robust. There's a lot of work that we need to do, and I shared with you some of the challenges here. And you can see here a lot of the technology that we're bringing to bear here, like the cell phone or the cellular technology, MIMO technology, we're bringing to bear microdoppler techniques in order to pick up fine tangential movements. Again, this is an imaging radar system that is going to be part of the system of tomorrow. Industry is evolving. If I look at the car company, I work for a tier 2. Many of you guys are tier 3s, right? You know, we're pretty far down on the food chain, you know, when it comes to this. But a lot of times, we're the guys that are bringing the most innovation to the party here. So in the past, I would work with a tier 1, which would then work with a car company, and I was discouraged to actually talk to the car companies, right? Because my tier 1 partner, you know, took that responsibility. But with everything that we're talking about, it's changing. And so now we talk directly to car companies. Now we talk directly to these disruptive groups like Waymo, Google, Uber, places like that. Because the issues associated with realizing autonomous driving are things in which analog devices and the people in this room can solve. You know, so again, this is very, very interesting for us. And like I said, you know, we can't do it alone. Those partnerships that I mentioned at the beginning, us being able to work together in order to drive the different types of technology that need to be matured, again, it's a great opportunity for all of us. Thank you.